So today we have Jaehong. We're going to talk about trustworthy and continually adaptable multimodal.
I will go. Yeah. I'm not opposed. Yeah, go ahead.
Cool. Thank you so much for inviting me. I'm so glad to introduce my research vision to UCF esteemed faculty members and amazing students. The title of my talk today is Trustworthy and Continually Adaptable Multimodal AI Systems. I'm talking about some key recent advancements that enable AI systems to continuously evolve in dynamic environments with the diverse multimodal inputs. And at the same time, these advancements should ensure responsible decision-making for safe and meaningful impact on the world. We're living in the era of the data explosion or data flood. The massive amount of the data are being generated every single day. These rich and diverse data sets aren't just collections of the information, but they form the very foundation for training today's most powerful AI models. What's striking is how this trend has become even more significant in recent. Over the past few years, the data growth curve has stiffened drastically. These trends become further apparent with the new RIPS dataset and benchmark tracks. So submission have more than quadrupled in just 2 years, reflecting a surge in the dataset and benchmarks in AI field. But this is just the beginning of the story. Even with our current massive scale, the hunger for more data continues to grow. So what's driving this endless pursuit of more information? Many factors behind this. For instance, we usually compensate for practical technical challenges, such as suboptimal training strategies or inherent architectural limitations, by simply scaling up the data for training. But there's another key reason I focus on. The world around us is constantly and repeatedly changing. AI systems aren't just dealing with static problems or fixed past knowledge. They need to continuously adapt to an ever-changing environments and evolving world knowledge. Just like the humans, we constantly learn from the new experiences and adjust to the world around us. In short, I'll highlight that AI intelligence also needs to keep evolving repeatedly and the constantly reflecting this world. So we cannot only rely on what it was initially trained on, but need to learn from the non-stationary data set, tasks, and environments constantly as the world is not fixed. Simultaneously, as AI learns, we should avoid to integrate the unethical or untrustworthy sources to maintain the reliability and the faithfulness. So ultimately, for AI to grow with us and remain aligned with the societal and ethical human values, it must evolve intelligently, learning the right things at the right time in the right way. As a long-term research goal, I've dedicated in developing trustworthy and continually adaptable multimodal AI systems from 3 major perspectives. First, I've worked on continual multimodal learning that enables the model to integrate the various tasks, data set, and even modalities throughout its operational lifespan, so they can generalize and grow over time. Next, to help models adapt beyond initial experiences and improve on diverse, fine-grained or long-horizon tasks, I've explored the post-training techniques, particularly through the adaptive training source generation. And lastly, I've been exploring how to ensure multimodal AI remains reliable and trustworthy. So this is crucial for safe and responsible use in the human interaction and the real world, or risk-sensitive applications. First, I've developed the continual learning of the multimodal models. Inspired by the human lifelong learning, continual learning is a research field growing in popularity, aiming for knowledge expansion of the models over time. So this is essential for real-world multimodal AI because it enables the model to evolve in dynamic and constantly changing the real-world scenarios. Formally, It aims to tackle a learning scenario where a model continuously learns multiple consecutive data sets over long time scales. So during training, when the model encounters new tasks, learning Zebra in here, the model transfers previously learned knowledge to solve new task problems. Here, we assume the model loses access to past data, considering practical issues such as data privacy and memory constraint situations. However, this restriction of data access critically causes undesired knowledge shift. For example, when learning about the zebras, a model might override previous learned features such as the tiger prints or four legs, replacing them with the zebra prints or hooves. As a result, it could forget essential knowledge from the past tasks. So to address this, many recent methods have focused on reducing these forgetting issues while progressively enhancing the model's capabilities. Adapting large-scale multimodal models to evolving environments through the continual learning is one of the major research fields in my joint research career. So specifically, I focused on the two key challenges: how to effectively integrate the new information in the continual learning, and how to prevent the influence of the undesired data during long-period learning. For the former, for example, I've tackled the key challenges like the adaptive memory control and a modular architecture expansion for scalable and structured continual learning. One notable work, dynamically expandable network, introduced a selective network retraining and adaptive network expansion so that the model can effectively accumulate the new knowledge based on their importance and difficulty while progressively expanding their knowledge without forgetting. So this work has been widely recognized and considered as a pioneering work that opened the field of the architecture-based or memory-based continual learning.
These are your papers?
Yeah, right. And next, I've explored integrating the many modalities simultaneously or over time, then the model adapts to evolving multimodal semantics. So this is achieved by the beyond the standard fixed cross-modal multimodal learning systems like the audio, video, audio text, or image text. And from the second perspectives, I've studied on the strategic training data selection to prevent the continual learner from learning some undesired data in their long period training scenarios. So, and similarly, the continual models must identify and remove some outdated information from the models. So this is the particularly important in case of the large language models because they have to track and keep their knowledge up to date based on following the change of the factuality in the real world. Among these, I'll introduce my recent work on building scalable and the generalizable continual multimodal AI from two key perspectives. The first one is that I'll discuss expanding capabilities of the vision language foundation models as the training data accumulates over time. And then I'll cover the strategies for improving the modality flexibility so we can enable the models to adapt and merge any modalities at any training time steps. Let's dive into the first chapter. While the idea of the continual learning is highly attractive, sometimes it has a critical gap to directly apply for the real-world scenarios. So it limits its practicality across the various realistic domains. For example, unlike the traditional continual learning assumptions, large-scale real-world data accumulates over time and remains accessible. So it's not the case that we can consider those tasks as some isolated ones. So that means we continuously deal with an ever-growing pool of the continuously expanding the open source or accumulated data set. The challenge is not just managing this data sequentially or separately, but dynamically prioritizing the most critical and helpful information for ongoing training. To address this, I reframe the continual learning through the lens of the continual data selection. Let's first describe the problem statement step by step. Assuming an ever-growing pool of the training data, new public multimodal data sets continuously released and incorporated into the data pool. but they may include a large amount of the undesired type of the inputs, which direct the task adaptation is forgetting to a much larger degree. My prior iClear 2022 work, online course selection, explored the way to filtering out such undesired training samples in an online manner for vision-based continual learning. So in here, we leverage the sample diversity and the relevance, which is guided by the granular level momentum for each samples to figure out which one is the much more beneficial or the necessary for enhancing the model's capabilities. And we generalize this idea for this real-week setting. Formally, given the importance score, do we identify and select the data points that are most beneficial for improving the model, and then train the model on these temporal subsets at each training round? So this continuous cycle of the selection and training allows the model to remain efficient and effective when the case of the model's data is accumulated over time. But this hides the two key objectives. The first, how do we effectively sample the data to learn? And how do we sample how do we manage the growth of this ever-growing data pool? Because as the data pool continuously expands, the processing all-importance core of this sample is computationally very, very expensive and often infeasible, impractical. So we have to deal with these two main challenges. In the first aim, how to sample the data to learn, I introduced one interesting observation that there's no universally works single metric for importance scores. So relying on the single important metric for those data selection doesn't work, particularly on the very complex multimodal scenarios. So on the left, we see the distribution of the ER trend scores across the various visual language tasks. And we see that the higher ER scores are more common in some tasks like the captioning, but generally shows the lower scores in average, like some certain tasks like the knowledge QA. This is important because ignoring this can lead to biased sampling, so which makes some model to overfit to frequently selected data set and disturb the model to generalize over multiple various tasks in visual language domains. So EL trend score, yeah, there is a good question. So the EL trend score is the one of the recent metric to measure the importance of the samples. It measured the ground truth, the L2, the prediction of the ground truth, and the let me explain it. So it compute the difference between the ground truth representation and the predicted representation by measuring distances as a L2 distance. So the lower distance indicates that it is much more have some much more similarity with the ground truth, and the higher distance indicates there's a lower similarity in the ground truth. That means the higher EL trend scores mean that we have to it is more valuable to learn because the model cannot predict it well.
So you're saying difference between ground truth and what the representation the model generated?
Yeah, right. It's a
how do you generate the ground truth representation?
So yeah, the ground truth representation is directly the ground truth of the ground truth of the prompt. This is a visual language tasks. So we have the ground truth answers, and we want to measure the differences between the predicted representation and the ground truth output. So it's kind of some classification differences for the geometrical distances.
So it's like embedding of
Yeah, it says prediction. So prediction is I can say it's a logic of the output.
CQA, right? So you have question and answer. Yeah. So of course you have a ground truth answer. So now tell me, so the model will predict the answer, and then you have ground truth answer. Then what you are
Right. Yeah.
I mean, the temporal now between these two.
Yeah, so it says differences in the embedding, text embeddings.
Yeah, that's what I was saying.
Yeah, that's correct.
So So then what is the, what is mean by density? What is it?
Density indicates that it's the sample distributions. So density means the sample, the count of the samples aligned with those specific Yanter scores range.
So ideally you want the difference to be zero, right? I mean, ideally you want to really as small as possible, the difference. And
So in this analysis, we can see that according to the different tasks, the effect of the specific certain importance score is different. So some important.
You want the score to be zero. Actually, I think what he's saying is you want the score to be higher because the high means the new data point is telling you something new.
That's correct.
So you want higher score.
Yeah, we want higher score, but based on using the single metrics, then we tend to select the certain tasks of the visual language the input. So the model should fall into some biased optimization rather than some. But for example, the knowledge VQA can be easily forget because the model do not tend to select those samples.
The problem you're facing is you're trying to figure out some new fact. You're trying to ask how much is it going to benefit your system if it adds this new fact to the data.
That's correct.
That is exactly the case because it looks like this is trying to explain the heterogeneity of the tasks. Different task has different distribution, which means there is no one solution. There is some sort of like continuous learning or different learning for different tasks, rather than requiring whether we want the score to be higher or lower. Just try to do that.
Yeah, so that's why we also show that the different important metrics has a different tendencies. Different tendency means that they have some different effect on the different tasks. So as shown in these cases, the entropy scores is much more generally high scores in the VQA and lower scores on other certain tasks. So the point we want to get this observation is that we want to use the different metrics for different some subtasks to make it to sample the beneficial information to learn this model when the case of we accumulate the data over time. Thank you. So yeah, building on these insights, I developed the Adaptive Infinity, an efficient and continually learnable multimodal IGE model. So this option aims to select the informative samples using the various data selection strategies in a combinatorial manner. So at each time step, new data is integrated into the training pool, and we allocate the entire data into the pool to the pseudo task clusters. And next, we select the information samples from each cluster for model training. So motivated by our previous observations, we propose a new multi-way data selection approach. So it automatically chooses the best scoring function for each cluster based on their discriminativity, which is measured by their entropy of the selected samples, so that we can ensure the skill balance subset of highly influential samples from the training data pool. We then train the model on this adaptively collected data set for enhancing the model's capabilities in a continual manner. And on the other hand, as discussed in the AIM2, when the data pool grows, computing scores becomes costly. So to manage this, we propose permanent data pruning. So in here, we calculate the pairwise cosine similarities within the pseudo clusters. So we can remove the redundant samples while maintaining their diversities. So in the end, we ensure the controlled and manageable growth of the training data pool, even during the long period training. We built our method on the multiple, the popular visual language benchmarks. So in addition to the LAVA 665 instruction training data set at initial training time steps, we consider the following order of the 5 the visual language tasks from the M3IT to the vision flag.
Can you go back? So what is this? So what is the T in what T is the U and what's the
Yeah, T indicates the time step. when the new data set incorporate into our entire data pool. So throughout the T0 to the T6, the model keeps learning, but the training data pool can be updated and become larger. So this is the scenario we assume that the new data set, new visual language data set are newly released and integrated.
So you have Lava 665, right? So that's a data set.
Right.
Okay. So you train your model based on that first. Yes. Then at time equal 1, you've got the M3IT data set. You edit that.
Right. So we have the M3IT plus Lava 665 data set into the pool.
So then you keep adding. So now you're saying from M3IT, you want to decide what samples to use to update the model. Is that the main problem?
No, not only for the M3IT, but it's more the selection of the entire training pool.
But I mean, you're doing incremental, right? Continuous. So you did that with Lava 665. Then you have trained model. Yes?
Yeah.
You got new data set, M3IT. Now you want to continue to learn. You want to improve your model based on this. And
yeah, that's the traditional continuing setups. Yeah. But we assume that the data pool is not separate or isolated, but we can have the larger data pool that open source data can be integrated over time. Then we have a training data pool with including the both Lava 665 and M3IT. And the problem is that changed to how can we select the beneficial samples from this pool for both?
Right. So you do that. Then what happens to are you saying that get all of these 6 together?
Right.
And select what train?
Right. That's correct.
Oh, okay. That's
so that's why the selecting importance and beneficial samples is important.
So the continuous learning, the tradition is defined that you have, you have 10 classes and you get 10 more classes. So is that like you are adding a certain task when you do this, or you continuous learning in terms of data, you just have more data, but it's not a continuous learning, right? Because if you have access to all the data, then it's not really continuous learning. It's just
so yeah, that's a very good point in view of the continual learning. So continual learning is I would say is a very broad field. Yeah. It's not certain the training strategies or certain the problem statement. Yeah. So one of the major problem statement is the thing that you said, we have the sequential data set and have access of the certain data set at the certain time steps. And we train these things while minimizing forgetting. But this is not applied, in some real world cases, it is not applied for directly because we already know that there's a lot of the open source data sets in the real world, in our case, especially for visual language tasks, and also new visual language tasks with the different tasks or partially overlap. Some earlier ones can be newly released. And then we would propose the scenario that how could we deal with modified the continual learning perspectives. So it is not exactly the same, but I'll say, that's why I'll say this is a continual data selection.
Okay, that's fine.
Okay, thanks so much.
We're doing some kind of sampling to select the most diverse samples at each particular step. The data selection step. So like in the first task, it is like knowledge VQA, and in some other task, it is like multi-image. So these tasks are very different in the quality of information. So how do you compare whether between different tasks?
Yeah, that's also very important point. So the question was how can we deal with the balance selection across the very different tasks in the visual language domain. So that's why we first cluster the pseudo task. We first construct the pseudo task clusters. So and we find the most impactful sampling selection strategies aligned with the specific pseudo cluster. So that's why we have some much more balanced and easily select the important samples compared to other samples within a cluster. So do not have some conflict across the different clusters and have a worry about the bias sampling. But when we use the single importance matrix, we suffer from those issues, because as we observed that the certain the tasks are much more frequently selected in the certain metrics. So we address these issues by proposing the multi-way data sections approaches. Cool. So we built our method on multiple, compare with the multiple data selection strategies, and show that our method achieves the superior performance in both terms of the average accuracy and the forgetting with the lower forgetting ratio throughout these continual data selection schemes. And yeah, in Adapt Infinity, we've explored the way to scale the large visual language models over time. And similarly, many multimodal AI systems are designed to handle only a limited set of the modalities. But we know that the real-world environments are increasingly dynamic, so require the AI to perceive the broader range of the modality inputs. This demand for more adaptable perception from the diverse signal continues to grow. For example, in embodied AI, autonomous vehicles, and medical AI domains, there's a lot of the very distinct sensor inputs, and we have to combine those knowledge into the single framework. But this is highly challenging. Even when integrating the multiple modalities, the popular and the strong multimodal large language model like the BELIEVE2 have the lower performance when they integrate the multiple modalities. So this is because the substantial complexity of the processing the multiple modalities in the single framework. So the big question should be, how can we enable large language models to integrate and reason over multiple different sensor inputs in a structured manner? To address this, I developed the CREMA, a generalizable and many modal reasoning framework and optimization strategy. So we can easily expand to integrate any new modalities at any training time steps. So I first mapped the different modality data into a unified representation space and extract the critical features for each modality through the newly proposed module architecture with the modality-specific adapters and the corresponding learner queries. And in addition, to mitigate the excessive computation when we integrate the new modalities into this framework, I developed the parametric fusion module. So specifically designed to merge and compress the core embeddings of the supportive modality informations using a self-gating sigmoid operation. As shown, the linear projection merges the supportive queries and followed by the attention by the self-gating. So in the end, large language model can process a manageable number of the tokens when in handling the dynamic number of the modality inputs in this framework. CREMA efficiently handles these diverse sensor inputs with the proposed the architectures, but we know that the differences in modality characteristics have a different quantity of the information. So this means that when we train this data at the same time, the model, a certain modality has some suffer from the overfitting or the underfitting issues because they have a very different the optimization conversion speed and optimization strategies or other bearing factors. So these capabilities, handling these capabilities is very crucial for both continuing and the various multimodal situation, especially where the some modalities are missing. So we can imagine that there's the temporal imbalance or certain type of the data drop out over time. So in this case, we have to effectively figure out how well the continual multimodal model learns on the certain modality inputs while do not affecting some other modality factors. So one way to address this, my CPR 2024 work, I introduced a sequential and a modality adaptive optimization. So by projecting the multiple input gradient onto the orthogonal subspace with each other, so we can develop the modality level, the sequential training. So model can optimize the certain modalities in their best manner while minimizing their interference or negative transfer from the other modality inputs. So this can make the models much more transferable and stabilized. And based on these ideas, we additionally propose the adaptive early stop strategy. So this is the aim for the enhanced training efficiency and adaptation. So specifically, we skip the training for certain sensory inputs if the model detects their convergence on those modalities. So it is based on this gradient-based stopping indicator. So if the certain modality is considered as already convergent based on their gradient level, some indicator, then we only stop on those corresponding modality weights. So as continue this process, we can converge much more faster and while make the computation much more efficient because we.
Are these figures real data or they are representation purposes? This rightmost.
Yeah, the rightmost things is that the indicator, the y-axis is the indicator, and we converge we consider the stressing modalities converged when the indicator reaches to 1.
Are these lines real coming from real experiments or are they?
Yeah, the real experiments. Yeah, it's from my real experiments. And the left side one is just I draw for better
So the
understanding.
meaning of it, that golden line goes on the longest, right? But the other one's already converged earlier.
True. Yeah.
So none of these curves are showing any convergence. Why?
Sorry.
So these lines, so are these stopping? So
Yeah, what
how
exactly
to
is that
interpret
when we
because
stop indicator?
with training epochs, none of the curve is settling down. So are they not converging? What is happening?
I think the question is what is exactly on the y-axis? What is early stopping?
Yeah, the only stop indicator is a much more complex, a little bit complex operation, but it's based on the proportional to the gradient magnitude. So when we consider the data is convergent when the gradient magnitude is sufficiently close to some certain threshold. So this is shown in the middle. So the threshold is represented by tau in here. So we measure the differences, the gap between the convergence threshold with their exact gradient magnitude, which are normalized as the 1.0, this indicator. So
the magnitude fixed for different modalities is different or same?
different. The magnitude, this tau is generalized. So it has used the same magnitude for across all modalities, but can be measured in their own manner.
So what is this saying that like a text will take both epochs as compared to like 3D and video?
Yeah, based on these results. Based on these results, we find that different, even when we learn the different modalities in the single framework, their convergence varies significantly.
In what situation, why text takes longer than like 3D video?
I would say it depends on the tasks. So because certain tasks, we have a more time to obtain the different information from the visual modalities. On the other cases, if the visual modality is pretty clear and the question might be simple, then the model tends to focusing more on the text information because this usually contains a much more dense information compared to the visual one.
For the convergence, correct me if I'm wrong, we want the gradient magnitude to be less than something. But we want it to be equal to 0.
Right.
Why it is stopping the opposite? It is like making it not converging.
It's the exactly same what we did, but this indicator is the term we want to show some inverse manner. So just make the exactly we did the same thing. That if the gradient level is the decrease to a certain tau, then we consider this is a conversion. But this indicator is the reverse operation. So it's a kind of this the magnitude scale is on the opposite side, so that we can have some inverse level of if the gradient level is a kind of the distance
Because here it says that exit, the gradient magnitude is greater than top, not about the figure over here. It is saying that when dictating the modalities, you will exit one modality, gradient magnitude is greater than top, which means if magnitude is higher, it has not learned that modality, then why would I would like to exit?
Yeah, it can be a little bit confused, but it's a real operation, real equation. But those visualization is to show that much more easier. It's kind of this converted term. So I would say those magnitude is larger than tau, and this operation is totally same. But it's a kind of this different type of the visualization.
But what's the intuition behind it? Like, what's the reasoning behind the extra modalities of complexity dividing circuits?
So you mean in my understanding, you mean why we have to add the extra modalities in this framework, or to show the convergence?
So the question is, why what's the idea behind introducing this new metric that you're saying is also complex and also graphs?
The prime question is why mix up all these things?
Yes, yes.
So of course, mixing up because maybe there's more interesting things you can do at the end. Right? So when you're mixing up, then you need to have some way to measure. So he's just giving you some metric.
Yeah, so the motivation or why it is really beneficial, then we can show some examples in the later slide. So it can be more beneficial to understand the situation in a different perspectives. So that's the benefit of the introducing the new modalities, even in the same the problems.
We have 1 minute left.
Yeah, okay, then let's speed up. So yeah, then in the end, our CRIMA shows improve the performance by incorporating the new modalities such as the optical flow, depth map, and surface normalization compared to other the multimodal large engine model baselines.
Thing is, but what's on the y-axis?
So y-axis is the performance on our benchmarks. It's based on the Bijan language tasks, Bijan language QA tasks.
What is 81? What is that?
Is a accuracy of the video QA tasks. Mm-hmm.
So in this one, you're saying that if you, so Blip2 typically doesn't use the optical flow, right? Just doing the image, but if you make optical flow, then it actually reduces, and then your method, if you take optical flow, increase and something normalization, then for the right, the message here is that you have a way to integrate multiple molecules in this typical image and the text that here we have made with the optical flow, certain normalization.
That's correct. That's exactly correct. So the existing multimodal large engine model is usually suffer from those integrating the new modalities and adversely decrease their performance when integrating them.
Surface normal, not like this.
Yeah, right.
Surface normal vectors.
Right. It's the different type of modalities. Yeah, so here's a visualization of the attention map across the different modality combinations. So given the question like is there first sound coming from the middle instruments, the piano, we can see that the multimodal large engine model struggle to find the correct answers when relying only on the audio and the video inputs. The attention appears very scattered and uncertain. But in case of our CRIMA, when we integrate the optical flow, for example, the model focuses more effectively on the dynamic regions, area of the motion. So we can allow the model to generate the correct answers based on those the human's motions or the corresponding interactions with the instruments. Okay, so we enable our models to continuously learn and adapt and allowing this process to make the model much more stronger over time. But so we're gonna plan to have some mini QA sessions, but we do not have enough time because we already allowed the questions in these earlier stages. So let's skip this part. So let's move into the second chapter. So we enable AI models to learn and adapt. But this chart shows that the data set scale for training will soon converge to the data scale on the internet. And similarly, at the UNC 2024, the co-founder of the OpenAI, Ilya, goes, there's only one internet, emphasizing the limiting factor for future AI will be data. And I believe the key challenge now isn't having the more data, it's about having the right data. We need to focus on the finding high quality and purposeful data that directly addresses the problems users really cares about. So these insights bring me to raise a second bullet on my research. In short, I have focused on addressing this challenge by the adaptively generating the training sources. So multimodal models achieve more diverse and meaningful experiences from those synthetic sources during their training. I first explored the problem of the text image generation, which is often built upon the large-scale pre-training, the fine-tuning, but it is also challenged that achieving the computational understanding of the visual inputs, often requiring the much more fine-grained data sets or some more better capabilities on specific generation skills. In here, skill refers to much more fine-grained capabilities, such as generating the specific object attributes or accurate object countings. So in this context, in my new 2024 work, Selma, I explored the method to teach these models by leveraging their own outputs. So which is kind of we can call the self-learning. And this is also strongly connected with the weak to strong generalization. That could be a key breakthrough for future AI toward the super alignment and self-evolving systems. In this framework, I first collect the skill-specific prompt, which within context learning of the large language models, by feeding a short skill descriptions and a few seed prompts about this specific skill to a language model, we can generate the diverse prompt to teach those skills. Given this collected skill associate inputs, the prompt, we generate the well-aligned training images by leveraging the text-to-image generation models, which is our target model to further improve. And throughout this process, we construct, or we can say like the self-generate image text pairs, which is specialized for diverse skills. And next, we fine-tune this T2I model on the multi-skill, the synthetic data set we just generated, using the skill-specific expert modules for focusing on those skill capabilities without hurting their performance affected by the other different task skills. So here's an example comparing with the strong T2I models, SDXL, and with the version fine-tuned with the Selma. And we see that our models much more super performance in the different skills like the text rendering or counting. This is achieved by expanding the model's capabilities by using by training the knowledges, expanding their knowledge based on their self-generated input. Then we naturally extend the earlier research question to the much more complex and long horizon task. So in this direction, I recently explored embodied continuing agent in Minecraft. This is the setting that we autonomically explore the simulation worlds and acquire diverse skills and make the novel discoveries. They start with very basic tasks for survival skills, like the gathering resources and crafting tools, and progressively master advanced strategies within this game's tech tree. Recent approach directly employs the large language models as a decision-making agent for reasoning, planning, and executing some specific actions in this RL agent. But this is very heavy computation. For example, crafting a pickaxe in the Minecraft requires a multiple prerequisites. For example, like the collecting wood and placing a table before making a pickaxe. And this each prerequisite triggers multiple and a sequential large language model queries. So these frequent queries slow down the execution and increase their cost a lot. To enable efficient decision making, we need to minimize those unnecessary large language model calls while maintaining the intelligence behavior. So it is especially crucial for complex skills, which requires multiple prerequisites and environmental adaptations. And I thought, can we create the adaptive training environments that directly help these RL agents focus on skills where they struggle at the most? So building on this motivation, I developed MGen, a method that uses a large language model only a few times to dynamically design those learning environments where the model can much more struggle with that and focusing on those capabilities for better enhanced skills. So we first analyze the agent weakness and adaptation, those the existing environments, and large language model can create by those customized environments based on their weaknesses. And in the end, by imagining and exploring those tailored environments, our long-term autonomous agents can progress beyond their past experiences or past capabilities throughout these learning cycles. Specifically, we first provide a large language model with a prompt composed of several components to generate the environments. And this is also including some feedback from the previous steps. And next, the large language model can generate the environment configurations, which is associated with the specific skills where the model is undertrained. And the configuration can be simulated into the training framework. Then the next step is to learn these RL agents on those customized the environments. So we trained on their models based on those skill associated environments. And after that, we measure the model's generalized capabilities throughout their original environments. And based on these results, we provide this result as the value of feedback and put them into the large language models like that. So we can further generate the new environments if needed to make the model much more have achieved the advanced skill or make some better capabilities to solve those long horizon tasks. So this can be done in the multiple cycles because we have the multiple capabilities and skills in this required in this RL agent. So for evaluation, we use the crafter benchmarks, which has 22 different achievements that an agent can unlock during their play episode. So for example, some of them can be very easily unlocked, like the collecting wood or collecting saplings. But some others, like the crafting pickaxe or collecting diamonds, may require the multiple prerequisites and environmental adaptations. As shown in this result plot, where the blue curves represent the baseline PPO model, and our MGen enables much more accurate and stable learning of the simulation work. So we see that we have a much more lower variance of the performance with the earlier conversions of to achieve the collecting the pickaxe or crafting other tools. And this illustration additionally showed that how MGen works. So if an agent struggles with the collecting coals, then the next cycle introduced a much more mining focused environments so that the model can easily learn those the collecting coal situations. And after that, if the crafting tools remain a major challenge in this agent, then the environment can adjust to provide a much more easily, the key resources much more easily. So in the end, the model can have some better capabilities compared to the other agent that just learned their original environments. So far, we've explored how the model can continuously learn from the large scale and the multiple modality data over time and expands the model's capabilities beyond their past or original experiences by integrating the adaptive training sources or environmental generations. So this feedback-driven approach helps the model to evolve with the ever-changing environments and making the model AI models much more flexible, generalizable, and powerful. But it is very important to keep in mind that this learning, evolving, or adapting do not guarantee their trustworthy or their reliability or their ethical the ethical issues. So without oversight considering those, AI trends on those evolving data may have encountered some serious consequences. So in real, many web-collected and synthetic data sets contains untrustworthy or unethical data sets. And these critical risks should be addressed before scaling the continually adaptable multimodal systems. Because when these flow data sets are integrated into the training systems, then the model doesn't observe these biases, but they have to amplify these biases over time. So this creates a pretty vicious cycle. The model keeps learning and observing more biases and gradually becoming the less trustworthy. Therefore, the next generation of the continually adaptable multimodal systems must not be only powerful, but also have to be fair, responsible, and aligned with the human values. So this is the last chapter of my research period. How can we build the trustworthy multimodal AI systems? So we can ensure the new knowledge along with the ethics and the safety while becoming more and more intelligent over time. So this is especially crucial in the high-stake environments or high-stake applications, like the autonomous driving, healthcare AI, or AI for legal decisions, where the unreliable decision makes some severe consequences in the real-world scenarios. So from this perspective, I briefly introduced the two primary works, enhancing the reliability and the faithfulness. But let me quickly go through.
You are after safety.
Yeah, I'm the.
We discussed this paper yesterday.
Oh, really?
I asked you twice.
Yeah, it's same.
Yeah,
So
so why
that
did you say?
just means that your student is unreliable.
Yeah, that is the one of the most my recent work, yeah, which is susceptible
Okay,
to.
so I think that it's very nice,
Mhm.
very good. So let me just conclude, let's show us last slide.
All right.
Other people are- I mean,
Cool.
very convincing. You have done so much work, so many
Mhm.
citations, very, very impressive. I'm not, I don't know how you have done it.
Mhm.
Yeah, my question was gonna be, who is the team behind it? Where are all the co-authors?
Aha. Yeah, so I primarily collect the most work as the first authors. So the co-authors are really engage me a lot, and we have a very valuable discussions to develop this work much more complete, and this direction is much more Mhm. Right.
So you're talking about all the work you did for PhD and the postdoc, is that right, or just postdoc?
It's combined.
Combined.
So several things are done in my PhD period, and others are done in my postdoc period.
Okay, good. Yeah, so I think it's good. So just go to the last slide and that's.
Yeah. So yeah, let me conclude very quickly. So I would say I bring the unique perspective that combines the continually adaptable multimodal systems with the trustworthy AI development. Models can continuously expand their intelligence over multiple dimensions like the tasks, data, modalities, and as well as time. And their capabilities are further advanced through the lens of the post-training with adaptively generated training data or environments. So model can grow beyond their initial experiences, initial knowledge, and learn from its own imaginations. And additionally, I would highlight that the risk of the unfiltered data or unethical, untrustworthy model outputs. So my research introduces a much more structured, scalable approach to evolving AI models so that we can ensure that this AI remains reliable, ethical, and believable, which is consistent with the human values, human ethics. So here, I'm pursuing the three main focus areas over the next 5 years. The first one should be the scaling the continually adaptable AI with the diverse knowledge sources. The second one is reliable adaptation and actions to OOD scenarios. And the last one is the much more the application parts, the trustworthy and private multimodal medical assistance. So for the former, the scalable multimodal AI to be continually adaptable, we must integrate the very diverse knowledge sources. AI should learn not only from these ever-changing words, but also from the prior knowledge, as well as the retrieve information from the external databases. And at the same time, multi-agent cooperation could further boost the knowledge boundary of the single agent by assisting by the other continual learnable agent as an indirect experiences. And the second part, along with these such ever-growing foundation models, as we just discussed, I also aim to enable these embodied AI models to react reliably and appropriately to unpredictable situations or user demands. So combined with the diverse technical extensions, along this actionable embodied AI allows the much more rapid and real-time adaptation to new environments based on the user request. And this can be also done in the multi-hop interactions and a continuous reflection with the surroundings. So I believe these capabilities will be also key innovations with home assistance, industrial, or rescue AI systems. So it'll be pretty exciting to go further in the near future. And lastly, I envision the trustworthy and private multimodal medical assistance. It'll integrate diverse inputs like the medical imaging, patient histories, and lab results, sensory data at the same framework. And building on my expanding research experience in the many modal reasoning framework, I'm currently leading one of the major components of an NIH-funded project aiming for the advancing health research through the ethical and the multimodal AI. So this is the end of my presentation. Thank you for listening. And if you have any questions, please feel free to let me know.
Some of the things like say blood, which is safe in like the medical context, might not be safe in the context of violence and everything. So when we are doing like continually integrating tasks and other modalities, how will we like ensure that it's safe, it's still safe while that it's not getting confused between the blood from violence or blood from the medical.
So you mean in my understanding, your question is like how can we integrate the continually adaptable learning systems into the medical domain?
Like not in the medical domain, but the different context, right? Blood is like in violence, we don't want to have like it's unsafe. We don't want to have like an image with blood or like violence out of it. But if I'm like a doctor, I want an image of like blood out of it, like to teach something. So how will I ensure that it's like trustworthy and like how do I?
Yeah. That's an important point. So I think at least we have to provide much more interpretable way about the agent decision, especially in some pretty sensitive applications like the medical domains. So in that sense, in my recent leading project in the NIH-funded one is not only focusing on some enhancing the model's performance on the benchmarks, but provide a much more interpretable the process why the model make those kind of decisions. So in this case, we can combine we aim to localize the certain parts of the input data can be contribute to make those kind of decisions. So it is not fully used for some automatic predictions, automatic some symptoms explanation, but can be used for assistance. So the doctor experts can use them as an assistance factor based on those not only for their prediction result, but also relying on their the contributions on the specific inputs, so that have a more dense information we can provide to the experts to help their decision makes a much more concrete or reliable. So those are ways that we can currently consider to use these multiple medical systems.
Safety criteria based on context. like, like legality, or how would you like determine where it's being evaluated? For safety criteria, like there is context, but even within that context, how do you determine the safety?
Yeah, that's also very important point. So how can we determine the what is the safety in the what is the contained in the safety criteria? So it generally it uses some predefined criteria like the pornographic or the abuse, animal abuse or terrorism and so on. This is one of the typical used benchmarks in this safety domain. But it is not restricted to those domains because the ethic values in the human society can be evolved over time as well. So we need to build, in that sense, we need to build a much more robust and flexible to control those, the criteria to be banned or to be avoided. So in our previous work, safety, including the safety, we can have some room to determine those some concepts to be avoided in a very flexible manner. So user can include their own criteria. This cannot be only for the general safety. This also can be utilized for some personalized information or privacy issues. So those concepts can be easily determined and extended based on their user demands or some industrial requirements.
Say for the toxic subspace, is that dynamic where the user, like, they can choose? Is it the initial default for the toxic subspace?
Yeah, that's correct. In safety, we first predefine the toxic subspace we want to avoid, but this can be very easily constructed instantly based on the user request or based on user some provided keywords. So we can control them very easily.
Thank you for the.
Thanks so much.
Okay.